Hi everybody, welcome to the 6.4a notes. There's going to be two parts to the 6.4 notes, but today we're going to start by talking about how we can represent functions with integrals. And so before we get there, we're going to just do some review problems. So this first problem right here says the integral of 0 to 1 of f of x dx. So remember, what an integral is asking for the area under the curve. But sometimes we just need to remember that the area under the curve, that phrase can sometimes mean above the curve too. Essentially what that phrase means is between the curve slash just like the function. In this case, we don't have a curve, we have straight lines. So between the curve slash function and the x-axis. And so this first section right here is asking us to find the area under the curve f of x, so this is f of x, between 0, my lower bound, and 1, my upper bound. So it's asking me to find the area between 0 and 1. And in this case, because it's below the x-axis, you're going to find it from the function to the x-axis. And if you guys notice, this is just a triangle. And so the formula here, because it's under the x-axis, whatever the answer is going to be negative because it's below. And then the triangle formula is base times height divided by 2. So our base is 1. My base is 1. My height is 2. So it'll be 1 times 2 and then divided by 2 because it's a triangle. And that will give us the answer -1. So the integral of 0 to 1 of f of x dx is -1. Our next section is 0 to 3. So it includes the section I have highlighted, but we're also adding this section on right here. So I automatically know that part of my answer is going to be -1 before it's simplified because that's this area. But now I need to find the area of this triangle. Again, base times height divided by 2. So our base is 2. Our height is also 2. We'll divide that by 2. And we'll get -1 plus 2, and that equals 1. So the area under the curve from 0 to 3 altogether is a +1 because we take away that -1 area. Finally, we have 1 to 3, so that's just this section, and we just did this work already. It's just the area of this, so it would be 2 times 2 divided by 2, which equals 2. And then for all of these, you can go through. This isn't really mandatory anymore, but add your units squared. But you kind of stop writing that eventually as you get through these more integral problems. So one thing that we can do is we can actually define functions by integrals. So if you guys see right here, I have this function g of x. It equals the integral 0 to x of 2t dt. And then h of x is the integral from -2 of x of f of t dt. So I want you guys to take a second and think, how do these integrals look different than the ones we've looked at this last week? Or how do they look different than the ones above? So one thing that you might notice, hopefully you paused and you thought about this, is that in all of these integrals, the top bound is actually an x instead of what we've normally been seeing as a value. So we basically don't know, in this case, what our second boundary point is, right? In these ones, we have a boundary point of 0 and 1, 0 and 3, 1 and 3. But now we just know that our lower bound is 0 and our upper bound is x. Our lower bound is -2 and our upper bound is x. And so essentially, right, what our area is going to be under the curve is dependent on what our second boundary is, right? Our second boundary could be a 1, but it could also be a 2, or it could be a 3. And so just so you know, you're going to see these, right? You're going to see them match up because x is our independent variable, right? And the area under the curve is dependent on what this x is. So let me give you guys one more example just to help you see kind of what I'm talking about right here. So I'm going to add this one right here. This is the function k of x, and I'm going to draw a little quick sketch. I'm going to call this f of t. So I know my lower bound is 1, so I'm going to write 1 right here. And so let's pretend, don't erase this or anything, but let's pretend this was a 2, right? If this was a 2, then now I would be finding this area. If this was, say, a 1.5, like if x equaled 1.5, I'd be finding this area right here. And so basically we don't know, in this case, we don't know what x is, right? It could be anything. So I'm just going to draw my sketch here. Say we have 1, 2, 3, and this is what I do want you to write down, right? This would be dependent, so like it would be dependent on the area under the curve, but let's just say that we don't know what it is. All we'll do is we'll say an x, and we'll say basically this integral represents the area between 1 and some x value. The x value could be 2, it could be 3, it could be 4. So that is what this notation essentially means. It means the area under the curve of f of t starting at 1 and ending at some unknown x value. And so let me give you a couple more examples to help this make more sense. So example 1 says g of x equals the integral from 0 to x of 2t dt. And it says this is a function, so it says that this function is a function defined by an integral. So g of x is defined by this integral right here. Fill in the table using that integral. So first, this is the function, right? Or sorry, this isn't the function, but this is like the function that we're trying to find the area of the curve under. So we're trying to find the area under the curve 2t. And you can essentially think about that as like, sometimes it's hard for us to, we're gonna have to graph here and it's hard for us to envision it when it's not x's and y's, but essentially we're gonna be finding the area under the curve of 2x. So what I'm gonna do over here is I'm just gonna go ahead and give myself a little sketch of what the graph of y equals 2x is. And I'm gonna be as neat as I possibly can. For my x-axis, if you look here, my x's only go up to 3. So I'm just going to go 1, 2, 3. And then for this case, I'm going to go up and I'm going to count to 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2. Okay, just like that. And so I'm just going to go through these. So let's say that I'm just going to like plug in like a normal table would plug in. So let's say that my x value is 0. This is how I would plug it into my function. I would replace x with a 0. And now this is trying to tell me to find the area under the curve 2t from 0 to 0. Well, that would just be, oh, I never graphed 2t. I need to do that real quick, sorry. But let's graph 2t real quick. So if it's like y equals 2x, it starts at 0 and then it goes up 2 over 1. Up 2 over 1, up 2 over 1. So the graph looks something like this. Okay, so if I'm trying to find the area from 0 to 0, like that's no area, right? Like 0 to 0 is just itself. So the answer to this one right here is 0. So when when x equals 0, g of 0 equals 0. Next one though is we're going to find the area from 0 to 1 in all of dt, 2t dt. And so that's this space right here, right? That is this space right here. That is the area from 0 to 1. And it's a triangle, so it's just going to be base times height. So the base is 1, the height is 2. I know it's kind of weird because my scale's weird, but 1 times 2, and then you have to divide by 2, is 1. So the answer to this one, I'll just write it out though. It's 1 times 2 divided by 2, so that's 1. The next one, my x value, so my upper bound is 2. So this is asking me to find an area from 0 to 2 of 2t dt, and in this case we're adding some more area, right? Now it's this triangle right here. So in our, this is the point 2, 4. So that means that the base is 2, the height is 4, and then we have to divide by 2 again because it's a triangle. So the answer to g of 2 equals 4. Last one, if you guys want to try it on your own, you can, but 0 to 3 of 2t dt, adding some more area in. This boundary point right here is 6, so this is 3, 6. So it is 3 times 6 divided by 2, and that equals 9. And you could keep going, but hopefully you can see now that you're just basically finding, when you're defining a function using an integral, you're basically just finding different areas under the curve at different boundary points. So let's go ahead and look at another example, and feel free to try this one on your own. So this says h of x equals the integral -2 to x of f of t, and this is a function defined by an integral. Find h of 1 and h of 2. So to do that, I'll start with h of 1. So h of 1 is going to equal -2. I'm replacing the x with a 1, f of t, and then this should have had a dt with it, dt. So I'm going to find the area between -2 and 1. So essentially we have a rectangle, and then we also have this little triangle right here. So I'm going to start by finding the area of the rectangle, so this section right here. So I have 3 on the base, and then right, 3, and then 1, 2, 3, 4, 5. So that section is going to be 3 times 5. And then I also need to find the area of this little space right here. The base is 2, the height is 1, so 2 times 1 divided by 2. that equals 15 plus 1, and so that means 16, so that means h of 1 equals 16. Now let's do it with h of 2. Negative 2 to 2 of f of t dt. Because we already know that the section from negative 1 to 2 is 16, we don't need to like redo all that math. We can just write 16, but I do now need to find this section right here because I haven't done that yet, and that's just 1 by 5. So plus 1 times 5, so my answer is going to equal 21 for that one. So those are how you do these problems, but now we're going to do a couple problems in context. So we're going to have some words revolved. So I'm going to read through this first, and I'm going to kind of zoom out here because we're going to need more than one at a time. So it says, you have taken over as a manager of a struggling umbrella company. Umbrellas are manufactured at a rate given by G of t equals 20t minus t squared. Umbrellas per hour for 0, which is less than or equal to t, which is less than or equal to 14. And t represents hours after the factory opens in the morning at 6 a.m. G of t is graphed below. So this is the rate. That's an important word here, right? It's the rate of these umbrellas being produced. Okay, so this is a rate curve. And 0, pay attention to that, starts at 6 a.m. So t represents the hours after 6 a.m. So just keep in mind that this is 6 a.m. right here. So we can do some more annotation in a second, but let's just go through and see what the problem is actually asking. But just keep in mind that the curve here is G of t, so it's 20t minus t squared. So it says, after a leisurely breakfast, you arrive at work at 9 a.m. Write an expression that gives the number of umbrellas that have been produced before you have even arrived. Cool. So one thing we talked about the very first day of this unit, we've talked about a little bit here, is that the area under the rate function, or the curve, right, however you want to talk about that, is the total accumulation of something. So because this problem right here says that this curve is the rate that umbrellas are being manufactured, the area under the curve represents how many umbrellas are being manufactured in that time. And so this says write an expression that gives you the number of umbrellas that have been produced before you even arrived. So we're going to go from here, right? We're going to use an integral because an integral helps us find the area under the curve. So we're going to write G of t because that is the rate curve, and we'll add a dt because we always have to have that. And so that is going to tell us the area under the curve, right? But we want to specifically know, it says write an expression that gives you the number of umbrellas that have been produced before you even arrive. And then if you look up here, it says you arrive at work at 6. So this company starts at 6 a.m. and so that's our 0, right? Because that's where it tells us, it says t represents hours after the factory opens, and then you get there 3 hours later. So this is a 3. And so that's what our first integral right there will look like. That is the area under the rate curve from 0 to 3. And then this says roughly how many umbrellas were produced during this time. So we can actually try to answer this question with what we just learned. So one thing to notice here is it doesn't tell us like how to figure out the area. So let's just talk about this real quick. We want to find the area from 0 to 3, which is like right here. Okay, and it doesn't tell us how we want to do this, but I do see that this is like really close to a triangle. And so since it doesn't specify which way we want to use, instead of using like Riemann sums or anything, I'm just going to use the triangle formula right here. So it's going to be base, which is 3, times the height. I'm actually going to plug in, I don't know exactly where this hits from estimating it, but remember I have an equation here. And so my equation that represents this curve is the G of t equals 20t minus t squared. And I'm just going to plug in 3 to that equation. So this is what's going to represent my height, 20 times 3 minus 3 squared. And then this is a triangle, so I'm going to divide all of that by 2. So if I do that, I will get 3 times 60 minus 9, all divided by 2, and then 3 times 51 divided by 2, and that comes out to be 76.5, and I'm just going to round up for this one. So about 77 umbrellas were then created during that time. Okay, we're going to go on to our next problem. Okay, so same graph. So I'm gonna have to kind of scroll up and down for here, so it'll be a little tricky, but we'll be okay. So Same problem, right? Oh, I added the graph. I was so smart. Okay. Same problem. It says now at 12:30 you break for a long lunch, right? An expression that gives the number of umbrellas that have been produced that day up until your lunch break. So the whole day, right? Up to your lunch break. So it's going to be really similar. S of t dt. The bottom bound is still 0. And then 6:30 would be 6.5 because that's 6 hours after they open. How many umbrellas were produced during this time? So now we're trying to find the area from 0 to 6.5, right? So that's this expression right here. And you know what? I'm just gonna use a triangle again because it doesn't specify. I guess maybe something. Well, okay, actually, let's walk it back. So we know already what this space is right here. So I already know what this space is. So I'm actually just going to find the area of this space right here. And this makes a pretty good trapezoid. So what I'm going to do here is I'm going to do 0, 6.5, S of t dt. And remember, this space right here we had figured out, we had estimated was 76.5. So that's 76.5. And then this looks like a trapezoid to me. So I'm going to use a trapezoid formula to find that. No Riemann sums, just kind of doing it based on estimation. So essentially the two bases are this one right here, which is g of 3, and then g of 6.5. And then my height is going to be 3.5. So it'll be 3.5 times g of 3 plus g of 6.5. And I'll use my equation to find that in a second, all divided by 2. And that's going to come out to be, I'm going to put some stuff in the calculator here, but 76.5 plus 3.5 over 2. And then I'm just going to go ahead and plug those into that original formula, 20t minus 2t, and I'll tell you what I get. So it'll be 20 times 3. Oh, I guess we technically knew that from the last problem, but that equals 51. So that's what g of 3 is. And then 20 times 6.5 minus 6.5 squared is 87.75. And if I now kind of add all of that together, times 51 plus this, I end up getting, if I put all of that together, I end up getting about 319 umbrellas. And so the question is, how does this come into play with what we've been doing right here? Like, how does this connect? So it says, write an equation, an integral for a function f of x that gives the number of umbrellas produced x hours after the company is opened. So we want a function f of x, right? And it wants an integral, right? So I'm going to go ahead and draw an integral. And it says that gives us the number of umbrellas produced X hours after the factory is opened. So we know that because it is asking for accumulation, I'm going to write my curve that I've been using. Oh, also, I don't know why I used S of t here. This should have said G of t. I'm sorry about that. So I'm going to write G of t here and then D of t. The company opens right at 0. We have this is right here is our rate equation. And then right here is going to be X, right? And this is going to stand for hours after 6 a.m. And if you wanted to go even further than that, I'm going to write it down here. But we technically know the equation for g of t this time. We know the equation for g of t is 20t minus t squared dt. And so that would be honestly an even more exact answer. So that's how this connects to what we're doing today. I hope you had fun taking these notes. I will see you later.